Hi there. Going to go over the review for the final Exam 7 that we gave you earlier. And this is under the General tab in our OneNote notebook here. So you see the General tab up there. And it's 132 version 7, or Exam 7 version 1. So looks like that. Let's add the word key to this. And of course, if you're watching this and you want to jump ahead and see, you'll be able to do that if you're not interested in the earlier problems rather than the later ones. Not a lot of room up here, so I'm going to probably jump down below the questions here, enter some space, work the answers. But some of them we might be able to do. So number 1 here, we have iron 3 sulfide reacting with gaseous hydrogen chloride. So that's iron 3 sulfide is going to be iron, of course that's +3, sulfur 2 minus, so that's Fe2S3. And that's reacting with hydrogen chloride, and that's in the gas phase. And that's going to produce iron 3 chloride, so that's going to be FeCl3, and hydrogen sulfide. Hydrogen sulfide is H2S, that's a gas as well. And we need to balance the equation. So we've got 2 irons, so we're going to need 2 FeCl3s. We're going to need 6 chlorines, so I need a 6 here, and that's going to give me 6 hydrogens and 3 sulfurs, which is exactly right for 3 H2S. So we balance that equation, and we're asked how much iron 3 sulfide will be required to react with 1.5 moles HCl. So we'd say 1.5 moles of HCl, and we want to get the iron sulfide, so there's 1. Equation starts here. This is, the hidden invisible 1. So 1 Fe2S3 over 6 HCl's, and those are moles. I didn't write moles there, but so 1.5 divided by 6, that's going to be 0.25. The second question here, we're looking at how much methane is remaining after 10 grams of methane reacts completely with 15 grams of oxygen. So what we're going to do is figure out how much methane reacts. So how many grams of CH4 is equal to 15 grams of oxygen. And we're going to convert oxygen to moles. So 32 grams of oxygen, 1 mole of oxygen there. Then we're going to use the coefficients in the equation, 2 and invisible 1 there. So 2 moles of oxygen and 1 mole of CH4. And then finally we'll do 16 grams of CH4, since that's the molar mass for every 1 mole of CH4. So that looks almost like I wrote 23 there. That should be 32. I guess that's the number of the problem. There's 32 grams of O2. Sorry, again, would help if I put it in the other space, I guess, so I'll move to that. So anyway, so 15 divided by 32, that's going to be a little less than half. Half of that's going to be a little less than 0.25. 0.25 times 16 is going to be a little less than 4. So I'm thinking it's probably, well, okay, that's how much reacted. We need to get how much is left, so we're not ready to compare it to an answer yet, but it looks like it's going to be a little less than 4. 15 divided by 32 divided by 2 times 16. That gives me 3.75 grams of methane that reacted. And it were nice not to put that as an answer down here. We had 10 grams initially, and that gives us 6.25 grams as our answer there. All right, so we're asked here in this question to do a calculation, and we can do it kind of quickly and conceptually. We're asked how many grams, which compound is going to contain the greatest number of atoms in 1 gram of that compound. So the number of atoms is going to be 1 gram. Then we're going to say 1 mole over the molar mass in grams. And then we're going to say Avogadro's number, which is a constant, over 1 mole to get the number of molecules. And then we're going to have the number of atoms per molecule. So what we're looking at here, if we look at basically the idea is the number of atoms divided by the molar mass for each one will be what we're dealing with here. So here in CO, we've got 2 over 28. C2H6 over here is going to be 8 over 30. C6H6 is going to be 12 over 78. And krypton is going to be 1 over 83.8. So I think it's pretty clear it's not krypton. I think that in all likelihood our winner is going to be the C2H6. If you calculate those numbers out, I think that's what you're going to see there, is that 8 over 30 is bigger than 12 over 78 or 2 over 28. All right, next up we have a reaction where we're mixing nitric acid with magnesium nitrate, and it's going to give us a solution with the concentration of a nitrate ion at half a molar, and we're asked to know what the concentration of the nitric acid must be. Okay, so we have a little complicated problem here. Let's get some space down here and talk about this one. So number 4, right here, we got 200 milliliters of HNO3. We don't know what its concentration is. We know that we've got 300 milliliters of magnesium nitrate, and we know that its concentration is 0.200 molar. Now, we know that when we add these two together, we'll have 500 milliliters. We know that that's going to be 0.5 molar in nitrate ion, right? So 500 milliliters times 0.5 molar is going to be, if I multiply those two together, I'll get 250 millimoles of nitrate. Is probably one good way of looking at that. We know, looking at the magnesium nitrate here, we're going to get 300 times 0.2. That would normally be 60 millimoles, but we're also getting 2 nitrates. You know, keep in mind this means 2 nitrates for every 1 magnesium nitrate. So 300 times 0.2 is going to be 60. 60 times 2 is going to be 120 millimoles nitrate. So we know that the remaining 130 millimoles of nitrate must come from the nitric acid. So if I have 130 millimoles nitrate and 200 milliliters, millis cancel out, we'll get molarity of the nitrate there. That's going to be I want to say 0.65, but let's use the calculator to make sure. Yeah, 0.65 molar. And that's nitrate ion, and that's coming from nitric acid. And again, there's, one nitrate, 1 mole of nitrate is given by 1 mole of nitric acid. So 0.65 molar HNO3 is our acid for that. So that calculation, the answer is B, and that makes a lot of sense if you think about it using that millimole technique that we developed later in the course. All right, so let's move on to number 5. A student wants to pair a solution with a final concentration of sodium ion as half molar and a final concentration of bicarbonate ion as 10th molar by taking some NaOH and some trona and diluting it with water. Okay, so let's see here. So again, we're not really looking at having a reaction here so much as a mixture. So we've got, we're diluting it to a liter. So we want in 1 liter, we want the sodium concentration to be 0.5 molar. And so that means we're going to need 0.50 moles of sodium ion coming from somewhere. The problem is it's coming from a couple of sources. And then we've got to get our bicarbonate as 0.1 molar. That's going to be the thing I think that tells us how much trona we need. That's again going to be the HNO3, so 0.1 molar HCO3 minus, sorry. So that's going to be 1/10 of a mole HCO3. We only get that from trona. So I think we're going to need 1/10 of a mole of trona. And if we have 1/10 of a mole of trona, that's going to give us, since we have 2 and 1 more, that's going to give us 0.30 moles, 3 times that much mole sodium, and again 0.10 moles HCO3, bicarbonate ion. And then we need to make up the other 0.2 of a mole with our sodium hydroxide. Okay, so that's the 0.20 mole in there. So our answer is going to be B. Again, we're going to get 0.20 mole NaOH, which is going to give us 0.20 moles of sodium ion. And again, so we're just looking at a mixture here, not a solution. All right. All right, let's look up here at 6. Now, as the concentration of an aqueous solution of sodium chloride increases from 1 molar to 2 molar, the value of which properties of the solution decreases. Okay. So the density of sodium chloride is going to increase as the concentration goes up. So that's increasing. Freezing point is going to go down due to freezing point depression. So the answer is B, 2 only. Number 9, a student using a coffee cup calorimeter to determine the enthalpy charge. He adds to both solutions. He forgets to put the lid on. The student forgets to put the lid on. That would cause what error in the calculated delta H value? All right, so our coffee cup calorimeter, right, the idea is that no heat's going to get in, no heat's going to get out. And everything we see is going to go from the system to the surroundings. And this is described as an endothermic reaction, which means that heat is going to flow from the surroundings. Okay, Q is going to go from the surroundings to the system. So the temperature of the solution is going to go down. Now, if we neglect to put the lid on, that means that heat from outside can go in and restore some of the heat that's in the solution. And that's going to make our temperature change is going to be too small. So if the temperature change is too small, Q is going to be too small. And so delta H should be reported low in terms of its magnitude. That is, not thinking about the sign, but thinking about the value. So too small, since the solution will absorb heat from the room, is the answer. C is the correct one for that one. Okay, moving on. Use some of that space up there. All right, we skipped, oh no, we did 12. Mixing a 1 molar aqueous solutions of these two things is going to give us a colored precipitate. So the first question is it going to give you a precipitate? The second question, is it going to have color? And while we're going to get some precipitates with the, this is going to give us barium BaCO3 solid, and this is going to give us CuCO3 solid. These two are both no reaction. They're not going to give precipitates. Acetates tend to be soluble. Question is whether the barium or the copper will give us color, and the copper has the partially filled d orbitals, which means that copper will give us color. Barium does not have any electrons in the outermost d orbitals, so it's not going to give us color. So this is the partially filled d orbitals in the copper is how we know that's going to give us a thing. This is copper plus 2. Copper plus 2 is, periodic table here. Copper plus 2 is D9. So its d electrons are probably going to look like this. And you have the ability of an electron from here to get moved up to there, and that's going to give you absorption of light and color of that complex. All right, number 9 asks us to determine which liquid has the highest vapor pressure at 25 degrees C. So highest vapor pressure is going to be the weakest IMFs. Right, is what highest vapor pressure means, it turns out that if you take a look at this, while you've got some LDFs and IMFs, and dipole in these, LDF only here, LDF plus dipole here, and LDF plus dipole here. It's kind of misleading, because the chlorine has so many electrons. The LDFs in carbon tetrachloride are actually stronger than the LDFs plus the dipole in the CFCl3. So this is the correct answer there. All right, so we're looking at problem 10, renumbered there, the sample of cyclohexane introduced into an evacuated container below its boiling point. 1/3 of the cyclohexane is in the form of a liquid, 2/3 is in the form of a vapor. The volume of the container is then doubled, maintaining the temperature at 40. What happens to the pressure as the volume is doubled? So we've got our container here. We've got our liquid and our gas. And then we double that container. We pull, say if it's a piston here, we pull this piston out so that the volume is doubled. Now, what's going to happen to the pressure? Now, will there be any liquid still left? I think that since 2/3 of the vapor occupied this volume, that the rest, when you expand it, the vapor, there actually will be no liquid left. It will all be in the gas phase. Right? So let's say if this is 1 mole, so 1/3 and 2/3, and this would then be 1 mole of gas only. Okay, so 2/3 mole of gas, 1 mole of gas. If we call this volume, let's say this was 22.4 liters. This would be twice that, 44.8 liters. Just 22.4 liters, because that's the volume occupied by a mole of gas at STP. So the volume has doubled. However, the mass that's present in the gas phase hasn't doubled. It's gone up, but it hasn't doubled. So basically what we're looking at, let's make this simple. Let's just call this guy 1 and 2. It doesn't matter what we call as long as the second one is twice the first one. Will be a lot easier. So our pressure in the first one is going to be proportional to 2/3 or 1. Our pressure in our second one is going to be proportional to 1/2. So 2/3 is 0.67. 1/2 is 0.50. So the pressure goes down by 0.17. Is that 25%? It's close. That's the thing it's closest to, I think. So the pressure is going to go down by about 25%. All right, number 11 here. Boiling points of ammonia, water, and hydrogen fluoride increase in this order. Ammonia is the lowest. Hydrogen fluoride's next. Water is next. Okay, so we're talking about intermolecular forces here, and the strongest one's going to have the highest boiling point. And if we look at these compounds, they're all able to do hydrogen bonding. So that's going to be a big factor in their boiling points. The London dispersion forces are not going to be that different. If I look at NH3, HF, and H2O, London dispersion forces are proportional to the number of electrons. So NH3, nitrogen has 7, that's 10 electrons. HF has 10 electrons. And water has 10 electrons. So I'm going to suspect that their London dispersion forces are about equal. In terms of their dipoles, I would expect HF to have the strongest dipole. This is probably going to be number 1. Water would probably be number 2, and then H3 would be number 3. HF is, of course, fluorine's the most electronegative element. Water's next. Nitrogen's not third, but it's third in this group. So I think that probably this explains that HF has got a stronger dipole force, probably explains the HF being a higher boiling point than ammonia. But the really much higher boiling point of water is probably going to have to be explained by hydrogen bonds. So again, I'm going to go with A on this one. So this is going to, again, they can all hydrogen bond, but water's got 2 hydrogens and 2 lone pairs for each molecule, so it can do a lot of hydrogen bonding. Water doesn't have a stronger London dispersion force. Water doesn't have a larger dipole force. And I don't think the hydrogen bonds are stronger. There's just more of them. All right, which gas has the smallest molar volume at STP? The volume occupied by 1 mole at STP, that's a weird question. I think that this actually gets into the issue of deviations. From ideal behavior. Normally we would say that the mole of gas at STP occupies 22.4 liters, like I said. So ideal gases, the molar volume is 22.4 liters per mole, right? Now, when you look at deviations, you're looking for strong intermolecular forces, and ammonia has strong intermolecular forces. It can hydrogen bond, etc. So it's going to deviate from ideal behavior and thus have a smaller volume. So pretty sophisticated question here. All right, over to 13 here, we're looking at trying to get the standard enthalpy formation of C2H2. That's ethine or acetylene. That's going to be the energy for this reaction. Carbon, 2 moles of solid carbon in the form of graphite plus 1 mole of H2 gas going to C2H2 gas. That would be our equation we're trying to get that for. So what we're going to do is try to put these equations here together in such a way to produce this. So we have carbon in the first one here. I'm going to take this one and do it times 2. So I'm going to say 2 carbon solid plus 2 O2 goes to 2 CO2. And my delta H for that is going to be 2 times this one, so 2 times negative 393.5. So that's going to be, go ahead and calculate that out, about 800. So it's negative 787 for that one. Then we need to get our hydrogens here. So and I just need one, H2 gas plus 1/2 O2 goes to H2O liquid. And that's going to be just as written, negative 285.9. Now, if I turn this one around, okay, so if I do this one times negative 1, and I'm going to flip it around, I'm going to have 2 CO2, that's going to cancel that out, plus 5/2, that's 2.5, I'm sorry, it's 2 CO2 plus H2O, sorry, got ahead of myself, it's going to cancel that one out, and it's going to give me my C2H2 plus 5/2 O2, that's going to cancel out my O2s here. So this all sums to our target reaction. This, since I'm turning it around, I'm going to do negative 1 times that, so it's going to be positive 1229.6. So if I sum those up, I'm going to get my delta H formation for this is going to be 156.7, and that's going to be positive. That's the answer C. And this is what I'm getting down here. I'm just not going to rewrite it. That's what we've gotten there. Okay, now we're looking at number 14 here, the new numbers. We're looking at the entropy increase, and so we're looking at estimating entropy. We usually look at the change in the moles of gas, right? So delta S is approximately equal to the change in the moles of gas, which is going to be the sum of the moles of gas for the products minus the sum of the moles of gas for the reactants. So here I have 1 minus O, that's plus 1. Here I have 0 minus 0, 0. Here I have 1 minus O, that's plus 1. Here I have 1 minus 1 is 0. Okay, so it's got to be one of these two right here is going to be our largest entropy. Which one is it going to be? Well, C, we're going from liquid to gas. A, we're going from solid all the way to gas. So our starting point in terms of order is much more ordered in A. So A is going to be our answer. That since it's solid to gas, we're going to pick that as our greatest increase in entropy. All right, looking on to problem 15, 2 gram sample of the rubidium perchlorate is added to 100 grams of water. They're both initially at 20 degrees C. The final temperature of the solution, they're both initially at 23. Final temperature of the solution is 21.56. What's delta H of the solution? What happened here was our delta T is 21.56 minus 23.00 degrees C. And temperature went down almost 1.5 degrees. Looks like negative 1.44. Let's check that out. 21.56 minus 23. That can't be right. Try that again. 21.56 minus 23. Yeah, negative 1.44 degrees C. Now it says we're assuming that the heat capacity of the solution is the same as that of pure water. Neglect the heat capacity of insulated container. So the heat that was absorbed from the water, okay, so what happened to the water is that our 100 grams of water with a heat capacity of 4.184 joules per gram times degrees C had this delta T change right there. So the water gave off water gave off 602.5 joules, just to round that off to a convenient point there. So if the water gave off 602.5 joules, that means that the heat of solution is going to be the heat that was absorbed, well, given off by absorbed by the rubidium perchlorate, so the 602.5 joules divided by the moles of rubidium chloride. So we have to figure that out. So using this and this, we're going to get moles. This 2.00 grams over 184.92 grams. So 2 divided by 184.92, it's going to be about 0.01 moles, I think. Yeah, 0.0108. Maybe 0.011 moles. So we'll say 0.011 moles. All right, so if I take 602.5 and divide that by 0.011, I get our delta H of solution is 54,772 joules per mole. If I make that as kilojoules, that's going to be 54.7 kilojoules per mole. And the closest answer to that is D, which I'm going to go with. Probably the error is in the, and maybe I should have included the rubidium here and made this 102. That's always an issue. Do you count that stuff you're dissolving as part of the solution or not? But it's close enough that I'm going to go with answer D there. All right, for question 16, we are looking at a plot of delta G over T versus 1 over T, and delta G versus T, and they're both linear. Okay, so let's think about that. So delta G equals delta H minus T delta S. If I divide everything by T, I get delta G over T is equal to delta H over T minus delta S. So if I plot this as, if I plot 1 over T as X, right? So let's see, let's rewrite that. Delta H, 1 over T minus delta S. So if I plot this as Y, plot this as X, delta H is the slope, and negative delta S is the intercept, right? So the fact that that tells me that that is linear tells me that delta H is independent of temperature if that graph is linear. If I look at the original version of the equation, if I do delta G is equal to delta H minus T delta S, now if I'm plotting delta G as Y, T as X, M is negative delta S, and B is delta H. If that's linear, that's telling us that, well, actually, it doesn't tell us anything, really. It doesn't tell us that delta S, well, no, it does. It tells us that delta S is independent of temperature. So if delta H and delta S are independent of temperature, So that's what the second graph tells you, is delta S is independent of temperature. Now, the fact that it's linear, that doesn't mean linear with the slope of 0, right? It can be linear with the slope of negative delta S, whatever it is. So delta H and delta S are independent of temperature. Delta G is still not going to be independent of temperature because it's equal to delta H minus T delta S. And so as long as delta S isn't 0, then the delta G is still going to be dependent on temperature. So delta H, answer B, is our correct answer there. All right, moving on. Elemental tin forms two allotropes, white tin and gray tin. For the conversion of white tin to gray tin, delta H is negative 2.02 and delta S is negative 7.04. What statement best describes the stability? All right, so white to gray. It's essentially a phase change in tin. It's not going from solid to liquid. It's going from two different versions of solid tin that have different properties. We know that when the point at which these guys are going to be in equilibrium is where delta G naughts, or rather, where delta G equals 0 is going to be their transition temperature. And again, you're going to have delta H minus T delta S. And so we looked at this kind of process before and saw that we could get that T is going to be equal to delta H divided by delta S. So if we take negative 2.02 kilojoules per mole and divide it by negative 7.04 times 10 to the negative 3 kilojoules per mole Kelvin, okay, that is going to give us a temperature value in kelvins. And of course, you had to make this conversion right here to kilojoules for the entropy because they're in different units. And then to compare our answer to the answers on the sheet, we're going to have to do a unit conversion. So 2.02 divided by 7.04 times 10 to the negative 3 gives me 287 Kelvin, basically 286.93. That is, if I subtract 273 from that, that's going to be 287 minus 273. It's going to be about 14 degrees Celsius. And so 13.8 is the value. I will do that. The one that's stable below is going to be the white tin, and the one that's stable above is going to be the gray tin, the way we have the reaction. So is that right? Let's think about that. We think about our graph of delta G versus T. Which one do we have here? We have a negative delta H and a negative delta S, so it's going that way, right? So actually, yeah, I'm sorry, I've got this back. Below that temperature, it's going to be the gray tin. Below the temperature, below this, delta G is negative, right? So that's going to favor the gray. And above that, delta G is positive. That's going to favor the reactions, the white tin. Okay. All right. Looking here at a plot of some kinetics data, we've got a reaction going on, and we're monitoring the concentration of A. And in the first 10 minutes, we basically went from 0.6 molar to right about here. I'm going to call that about 0.3 molar maybe. And this is 0.6 molar. So our rate is going to be 0.6 molar minus 0.3 molar over 10 minutes. 10 minus 0 technically. That's going to be 0.003. And when we do that math there, just simply we're assuming that these 2 points, that are straight, that you have a straight line there between those 2 points, and you get your slope of that line. And when you say rate of disappearance, that means it's going down. That takes care of the negative sign that you would normally see associated with that. All right, number 19. An irreversible reaction, A, B plus products is A plus B equals products is monitored in a buffered solution. Okay, so that means the pH is constant, where B is much greater than A, by measuring the concentration of A as a function of time. The decay of A is found to be first order, with the half-life varying as shown. Okay, so depending on the pH of the solution, our half-life changes, and also we've got different concentrations of B. All right, so the half-life is inversely proportional to the rate, right? The rate constant. If the half-life is going from here to here, that means the rate's doubled, okay? And going from here to here, the concentration of B doubled. So if the rate doubled and B doubled, those tell me that the order of B is to the first. So anything that has B not to the first, we're going to get rid of. So those two are gone. Then we have to consider these two. We took a change in the hydrogen ion concentration going from 1.5 to 1.0, and we have to kind of back that out and see what the hydrogen ion concentration is. So let's do that. So remember, our hydrogen ion concentration is going to be 10 to the negative pH. All right. So this would be our hydrogen ion concentration. Then for this case is going to be 0.1 molar, and then 1.5. This is going to be 0.0316 molar. Okay, so from 0.1 to that value, we basically increased our rate by, in this case, we're increasing our rate by 3.16. Okay, and the half-life went from 60 to 190. So if I take 190 and I take the inverse of that, and let's see, this actually represents this change here. If I look at the rate for that, that's a 3.16 increase as well. So that tells me that the hydrogen ion is also first order. And so our answer is going to be A, that the hydrogen ion is first order, and that we have to get the B from the first two data points with constant hydrogen ion. And then if we look at the effect of the pH change, we look at that by calculating the hydrogen ion concentration, and we see that from, if I number these 1, 2, 3, going from 3 to 2, we went up by a factor of 3.16, going from pH of 1.5 to pH of 1. That's a factor of 3.16. And then our rate went up by a factor of 3.16. I get that by, since the rate is, inversely proportional to the half-life, I can say 190 over 160, and over 60, and get that 3.16, and so 3.16 to the x is only true, equal to 3.16 is only true when x is equal to 1, so it's first order. All right, so in our next question here, we've got a decomposition reaction. It's second order. We got the rate constant, and we're given the concentration initially, and we have to get the concentration after 20 minutes. So that's probably a good time to hop back and take a look here at our formula sheet and go up here and find the equation we need for that. So our equation for a second order reaction is going to be this one right here, right there. So 1 over AT equals KT plus 1 over A naught. So 1 over what we're trying to get, NaCl at time t, is equal to KT plus 1 over the NaCl initially. That's going to be our 0.043. This is our rate constant here. That's going to be that value right there. This is 20 minutes. We're going to need to convert minutes to seconds. So let's do that calculation. So when I plug that in, the answer I get is that NaCl is at time t is 0.036. That's at 10 minutes. I'm sorry, 20 minutes. That one thing I'm looking for there, that is lower than this one. So I'm going with the answer B there. All right, so I'm going to cut this off at this point, and then we'll pick up with the remainder of the test in the next video.